Okay, welcome back. So I'm going to calculate the center of mass of an extended object, namely a rod of length length L and mass M, mass capital M. So let's say I have a rod here, and it has a length. So here is the rod, and it has a length L, capital L, and the mass of the rod is capital M. And it's a uniform rod, just a uniform rod, meaning it doesn't get thicker or thinner. It's not like a baseball, just a simple rod. As you might guess, the center of mass will be in the middle, and I'm going to show you that that's the case. So let's draw our x and y axis. So here is the x-axis. This is the origin here. And since the mass of this rod is capital M, we will have something called the linear density, lambda, and it is the mass divided by length, the mass per unit of length. What it does is, let's say if I have a meter stick and it weighs a kilogram, if I take 1 centimeter, 1 centimeter is 1/100th of a meter, it will have 1/100th of the mass. So it will tell you how much mass is contained in a segment dx. So let's say here a segment dx. A segment dx, a segment of width dx, will have a mass of dx times this mass density. If you have the total length, it will be this density times the length, which gives you the total mass. So since only in the x direction, the x of the center of mass, the position of the center of mass, will be the integral of. It says here you have to divide by the total mass. Well, it will be divided by the total mass. The mass exists between 0 and capital L. Beyond here, there is no mass, and on this left side, there is no mass. So from 0 to capital L. And I have x, the position of each piece here that has a mass dm is x. You might say, well, it has dx. I mean, are you talking about the position to the right side or to the left side here? But the truth is, when you shrink it to 0, the left side, the right side, there is no difference. It's essentially to them. It's like if I ask you, what's the distance from here to San Francisco? You might ask, is it from my right hand or from my left hand? Is it from here? Is it from me to San Francisco or from the door of this classroom to San Francisco? The answer is it doesn't matter, because distance is vastly more than little ones don't matter, especially when they're shrinking to 0. So x times dm. All right. So I have 1 over capital M times the integral from 0 to L. What is dm? Well, dm, how much mass is contained within a width dx? Well, dm will equal to capital M over L times dx. Again, imagine dx is like 1 centimeter, and this tells you the mass per unit of length. It tells you the mass per meter. So let's say it's 1 kilogram per meter, then a 1 centimeter will have 1/100th of that, 1 millimeter will have 1,000th of that. So you just have to multiply it by the width in consideration. So it will be m over L times dx. So I have x here, and then I have, for dm, I'm going to write m over L times dx. The capital M is constant, capital L is constant, so they come out of the integral. By the way, this cancels. And so I have the 1 over L comes out, and then from 0 to L of x dx. And the integral of x is x squared over 2, so I have x center of mass would be 1 over L times x squared over 2, evaluated between 0 and L. So I have 1 over L times, evaluated at, let me put the half here also. Evaluated at L, I get L squared, minus evaluated at 0, you get 0, and so you have L squared over 2L, which is L over 2. And as you would imagine, yeah, the center of mass is halfway at L over 2. By the way, it doesn't matter where you choose your origin, the center of mass will be at that same position. Okay. All right, that's great. Yeah. All right, let us go on. Okay, the next topic is rotational energy, which will introduce us to the concept of the moment of inertia, which plays a similar role in rotational motion as the mass plays in linear motion. So, for example, in rotational motion, we have, instead of position in linear motion, rotational motion, we have theta. We measure things with the angle. In linear motion, you have V. In rotational motion, you have omega. In linear motion, you have the mass. In rotational motion, we will have something called the moment of inertia. We will figure it out in a moment, what it is and how it's related to the mass and so on. So imagine you have an object here. Again, let me go back to my dumbbell, and here it is. Here is M1. Here is M2, and maybe here is M3, and here is M4, and the distance from the point of rotation to M1, I'm going to call it R1, and the distance from the axis of rotation to M2, I'm going to call it R2, and the distance from the axis of rotation to M4, I'm going to call it R4, and the distance from M3 to the point or the axis of rotation, we're going to call it R3. And imagine all of these masses are spinning, so they're just spinning. Okay, just like if I have my wheel here, here's the axis of rotation, and the wheel is spinning. Okay? We will figure how to calculate it for a wheel, but let me do point masses in a moment. So everybody is spinning, and since it's a rigid body, they cannot get closer to each other. Everybody has the same omega. They're spinning with an angular velocity omega. So what is the total kinetic energy? Total kinetic energy, well, it will be, as usual, it will be 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared plus 1/2, I should have chosen only 3, but let's continue, m4 v4 squared. Now, they have different speeds, because if you're farther away, you make a larger circle, so you're moving at a larger speed. If you're closer, then you're having you have to go around a tinier circle, so you have a smaller speed, but everybody has the same omega. And remember, V was equal to omega times R. So V1 will be omega times R1. So let's do that. So it will be 1/2 m1 omega times R1 squared plus 1/2 m2 omega R2 squared plus 1/2 omega 1/2 m3 omega R3 squared plus 1/2 m4 omega R4 squared. If you like, you can write it in summation notation. It would be 1/2 the sum from I equal to 1 to 4, in this case 1 to 4, and then mi omega Ri squared. So that's briefly what it is. And you see, it's already more convenient to write it in summation notation. So if it's m1, it would be m1 omega R1 squared. So you have 1/2 m1 omega R1 squared, and then keep doing this, repeat the addition until you reach 4. So we will square this and then pull the omega out. Before I pull it out, I will do it in 2 steps. So I have 1/2 I equal to 1 to 4, and so here I have mi omega squared Ri squared. You see, omega is the same for all of them, so it could be pulled out. It could be pulled out. So I'm going to write it this way. 1/2 of the sum of I equal to 1 to 4 of mi Ri squared, right, because it was R squared. And then the omega squared, I'm going to write it here. So in linear motion, we had 1/2 mv squared. In rotational motion, I have 1/2. Instead of linear velocity, I have angular velocity squared. So what should we call this? We call it I, the moment of inertia. So the definition of the moment of inertia, the way we're going to define it, is I, for a collection of masses, would be the sum of I equal to 1 to n of mi ri squared. And if you have infinitely many masses, again, if you divide your object into many masses, make the masses tinier, but make the summation go to infinity. So this goes to 0 and this goes to infinity. And when you add them, it becomes the integral of r dm, of r squared dm. And we're going to calculate the moment of inertia for extended bodies in a moment. So before we do moments of inertia for extended bodies, I'm going to do it for point masses first. So I'm going to do this example from the book. It says, students participating in an engineering project design the triangle widget seen in the figure. So we will show the figure. And then the three masses are held together by lightweight plastic rods, so they're rigid, and they rotate in the plane of the page about an axis or an axle passing through the right angle corner. And then what should the angular velocity, so that we have a rotational energy of 100 millijoules. So let me draw it for you first, so that we know what's going on. So let me get my drawing here. So here is the example. You have this mass here. It is 150 grams. And then you have another mass here. It's 300 grams. And then you have another mass here. So this is a 90-degree angle. You have another mass here. It's 250 grams. And this is the axis of rotation. They're rotating there. And so they will rotate like so. And the question is omega, what should omega be so that the energy, total kinetic energy, would be 100 millijoules. So let me describe it for you further. So let me name them M1, M2, and M3. Okay, just want to name them. This is the axis of rotation. Imagine there is an axis here, and they spin about it. So they're spinning like that. They're connected by light rods, and they're spinning about it. So you could go back and use the kinetic energy, but you will see the definition of kinetic energy. The problem is it's not very convenient. It would become not very convenient to go back to that. And you would want to use the inertia, the concept of inertia. So let's calculate, first of all, the moment of inertia. But I have to tell you those distances first. So this is, I think, 6 centimeters. And this one is 8 centimeters. This is 8 centimeters. Okay. So by definition, I will explicitly write this, the moment of inertia will be m1 r1 squared plus m2 r2 squared plus m3 r3 squared. But remember what r stands for. M1 is 300 grams or 0.3 kilograms. R is the distance from the mass to the axis of rotation. Well, M1 is located at the axis of rotation, so it's not far from it. It's at 0. So the distance from it to itself, which is the axis of rotation, that's 0. Plus M2, the distance from here to here is 6 centimeters, and M2 itself is 150 grams or 0.15. So 0.15 times the distance, which is 0.06 meters. 0.06 meters, right? Centimeters. Oh, don't forget to square it. That's a typical mistake. I make it too. And then M3 is 0.25 kilograms, right? And how far is M3 from the axis of rotation? It is 8 centimeters, or 0.08 meters, and you have to square it. So let's calculate the moment of inertia. So it would be, that's 0. And so you have 0.15 times 0.06 to the power 2 plus 0.25 times 0.08 to the power 2. That gives me a moment of inertia of 0.00214, 0.00214, and the units are, I forget to mention them, well, kilogram times meters squared. Kilogram meters squared. Those are the units for moment of inertia. So the total energy, total kinetic energy, will be 1/2 I, the moment of inertia, times omega squared. And the question is, what should omega be so that the kinetic energy will be 100 millijoules? The kinetic energy is 100 millijoules. Milli means times 10 to the minus 3 times, or equals 1/2. The moment of inertia is 0.00214. That's 2.14 times 10 to the minus 3. Let me write it this way, 2.14 times 10 to the minus 3 times omega squared. And the 10 to the minus 3 just goes away on both sides. That's why I wrote it that way, so it cancels. And so I have, let me see here, times this over 2 times 100. Then I have to take the square root to solve for omega. I get 9.66 or 9.67, 9.7 basically. So I get omega will be about 9.7 radians per second. If you work in SI units, you're going to get omega in radians per second. Okay, and that's it for that. Now, moments of inertia for extended bodies, they have to be calculated using the integral. And you have the moments of inertia for different bodies. So let me just show you on a. By the way, to calculate to tell me the mass, you just have to say it's 5 or 10 kilograms. For the moment of inertia, which goes here, you have to specify around what axis you're rotating. You see, the moment of inertia about this axis will be different than the moment of inertia about this axis. If I took this axis out and actually fixed it here and made them spin about this axis, the moment of inertia will be different. And the larger the moment of inertia is, it means it's harder to change the motion of the object, because just similar like the mass, the larger the mass, the harder it is to change its motion. For example, let me just show you let me show you an example. Here is a meter stick. If I hold it at the 50 centimeter mark and spin it, it has a certain moment of inertia, right? If I spin it about an axis about here, it's actually easier to spin it about this axis than to spin it about this axis. It's harder. When you hold it from the end, it's harder. So the moment of inertia, if I'm holding it from the end, the moment of inertia about an axis, imagine you drill a hole here and make it spin around it, versus drilling a hole in the middle and making it spin around it. The moment of inertia about the end is larger than the moment of inertia about the middle here, the center of mass. And so I'm going to show you how to calculate the moment of inertia for extended bodies using the integral. So remember, the moment of inertia was r squared dm, and that is the moment of inertia. If you have a sum, or if the sum becomes infinite, or if you have just a collection of masses, you have I1 to n of mi ri squared. So again, here are masses. So imagine you drill a hole here, and then you take the masses. So you take m1, and then how far is m1 from here? That's r1, and then m2, maybe it's here, and that's r2. And we just say, call one of them ri, call one of them mi, and the distance to it is Ri, and just divide it into many masses, right? Take this, it's like you take this and make it into a grid. Make it into a grid, and so you divide it into many, many masses. And if I say, what's the moment of inertia of this, you should not be able to answer. You should say, I don't know. You have to specify the axis. If you say, if the axis of rotation is here, then I'm measuring the distance to the objects, to the masses from this point. Or if I say, well, if I drill a hole here, what is the moment of inertia about this axis? Then you have to do the integral about this axis, and then do it. Actually, you don't, because we have a way to skip that. It's called the parallel axis theorem, which I will prove to you a little bit later. So let's take the one-dimensional case. Here is the rod, and I want to calculate the moment of inertia of the rod. First, about the center of mass, or the center of the rod. So let's say the rod here is of length L, and it has a mass m, and I'm going to spin it about this center, here. So here is the x-axis. And if I say, what is the moment of inertia if I'm spinning about here, right? Here's the x-axis. Well, we can calculate. So first of all, the moment of inertia would be, if the rod has mass m, and so that linear density, the mass per unit of length, is m over L, and so if you take a length of dx, it will have a mass, a dm will have a mass of lambda times dx, which is m over L times dx. So we have the moment of inertia would be the integral. Here, since I'm going just in the x direction, r is equal to x. There is no y component. So it's just x squared times dm. The mass exists between x equal to 0 to x equal to L. So from 0 to L. So I have I would be the integral from 0 to L, x squared. Well, let's just keep it as x squared. And then dm is m over L dx. So I put the dx here, and then I have m over L times dx. Let's calculate that. The integral of x squared is x cubed over 3, so I have 1/3 of m over L x cubed. M over L x cubed. Actually, I made a mistake. I'm sorry. Here's the mistake. This integral, let me back up. This integral that I set will calculate the moment of inertia about this axis, about here. So let me do the moment of inertia about here, since I started that. So what's the distance from the axis of rotation to this? That is r, or it is x. From here to here is x. Yeah. So I'm calculating the moment of inertia about this axis. So let's calculate that. So it's x squared times dm. Yeah. Looks good. Yeah, looks good. Now it's good. All right, so let's see. And I evaluate this between 0 and capital L. And I get 1/3 of m over L. And then I plug in L, so it becomes x cubed. And then when I subtract the 0, it's just 0. So this is just 1/3 m. L cubed over L is L squared. So that's the moment of inertia about the end. The moment of inertia I specify here about the end of the rod. How about the moment of inertia about the center of the rod? Let's do that. I will be more careful now. Here is the center of the rod. Here it is. And I'm measuring from here. So I will take my origin to be here. That's easier to deal with. So here is the negative x-axis. So since the rod is length L, so this is L over 2, and this is negative L over 2. So what's the distance? So if I take a dm here, this is a dm, and it has a width dx. The distance to it is also x, because I'm measuring from here. If this is 1 centimeter, it's 1 centimeter. And if I'm measuring here, it would be negative. So if you measure to here, and this would be x. So that will give me the right x. Whereas if I chose my origin here and I tried to measure the distances from to here, it would be a little pain to set the integral. So it's easier to do it this way. So I will have the moment of inertia about the center of mass in this case, about the center, will be the integral from where to where? Well, x runs from minus L over 2 to L over 2, L over 2 to L over 2. The moment of inertia says do r squared times dm. In this case, it's just x squared times dm. X squared times dm. So I have I about the center of mass will be the integral minus L over 2 to L over 2. X squared. What is dm? Well, dm is m over L times dx. Times m over L times dx. And so here, by the way, since x squared is an even function, I could just integrate from 0 to L over 2 and double that integral. And just double it because it's an even function. So it will be, I have the m over L, and I'm going to double it, m over L gets out, and then I'm going to double this and just integrate from 0 to L over 2. And then here I have x squared dx. So I have I, about the center of mass would be 2, and then m over L. Well, m over L, yeah, it just stays m over L times. The integral of x squared will be x cubed over 3, so it'll be 1/3 of x cubed, evaluated between 0 to L over 2. Again, you evaluated the upper limit minus the evaluation at the lower limit. And the lower limit is just 0, because you plug in 0 for x. And so you get what? You get 2 over 3 m over L, and then you plug in L over 2 cubed. And L over 2 cubed will be L cubed over 8. L cubed over 8. And so I have m, L cubed over L is L squared. And then what? Well, 2 over 8 is 1/4, and 1/4 times 1/3 is 1/12. So notice the moment of inertia about the center of mass, is larger than the moment of inertia about this end. And always the moment of inertia about the center of mass will be the least. About for an axis going through the center of mass, it will be less than any other one. It's a minimum, and we will show that. We will show how to prove it. Okay, so that is that. I want to show you also, because the book has moment of inertia for a hoop, the moment of inertia for a disk, the moment of inertia for a bunch of things. So I want to show you the moment of inertia for how to calculate the moment of inertia for a hoop, and then how to calculate the moment of inertia for a disk. All right. So I will do that in the next video because I'm running out of time on this one.